A prime responsibility for systems engineers is to identify emergent behaviors in complex systems, especially unanticipated chains of connection that give rise to serious problems. A famous example is the Fukushima nuclear incident in March 2011. The 9.0 earthquake did not damage the nuclear reactor, which was designed to handle it, but it did trigger a tsunami which flooded the basement backup generators, which stopped the cooling pumps, which allowed the reactor core to melt down and contaminate the local countryside. Model-based systems engineering addresses this need directly by creating a single model tying all of these elements together. But the challenge is that these elements may be spread over multiple tools and data repositories. Syndeia, the MBSE platform from Intercax, creates and manages a graph to connect these disparate models. But the scale of the graph for real systems may make it hard to see the critical chains of causation. Part of the problem is that these chains contain both intra-model connections, stored within the individual tools, and inter-model connections managed by Syndeia. Syndeia 3.1 provides a utility for demonstrating the potential power of modern graph database technology for finding and displaying extended connections. Both the intra-model connections from the SysML modeling tool, Magic Draw or Rhapsody, and the inter-model connections are exported by Syndeia to a Neo4j graph database. The user can interact with the database through a web interface using the powerful Cipher query language to ask both general and very specific questions. As a demonstration, we begin with a version of our UAV model, where we've created a lot of different connections to different tools. Now again, we can launch Syndeia, but in this case we're going to go down to a utility called SysML to Graph that does the export to a Neo4j graph database. Now this is the web interface for that graph database. And again, this is available to download for free for your evaluation. And at the top line, we have the command line where we can post the queries to the contents of that database. And the first query that we're going to do is simply to show us everything, to show us all the nodes and all the edges. And that gives us what is really kind of a hard to interpret diagram. In this case, there's over 1,200 different nodes and a larger number of requirements. So while this gives us a sense of the contents of the database, this particular query is not terribly useful unless we simply want a text dump of everything. But we can begin to be more specialized, more narrow in our queries. And let's go to a second one that we've staged up here, which is to show us every JIRA issue and what it is connected to. We're using what's called the Cipher query language here at the top. And so when we go ahead and we run this particular query on the database, we get a somewhat more manageable diagram. In this particular case, the yellow nodes happen to be SysML activities from the Magic Draw model, and the gray nodes are JIRA issues from the JIRA repository. And we see two different types of connections here. From the yellow node to the gray node, we see what are essentially intermodal connections, reference connections between the SysML activity and the JIRA issue. So from each of those activities, we would be able to go directly to the JIRA web interface, assuming that we have access to that repository. Between the yellow nodes themselves, we have what are essentially get behavior relationships. In other words, a decomposition of the central top-level activity here into sub-activities and sub-sub-activities. If we zoom out, we can see that particular pattern is that the SysML elements, the intra-model connections, are shown between the yellow nodes. So we have a way of connecting both across intramodel and intermodel connections and displaying those and finding those in a single query. And we can use these for a lot of different types of query applications. For example, we can say, here's a particular JAMA requirement, endurance. I want to see every SysML element, every SysML block, in this case, the aircraft platform block. which is connected to that JAMA requirement. In this case, the connection is indirect. The aircraft platform block is connected to a SysML requirement, which is then connected to its corresponding JAMA requirement. Now, in a case like this, sometimes we need to be a little broader. We're interested not only in the directly connected block, but in every other block that uses that, because they would be impacted by a change in the JAMA requirement as well. So in this case, we're going to look for that block and for the blocks that own that block. So again, slightly different query. We've expanded it. And the result shows now that we have a JAMA requirement for search capability connected to a SysML element, which is satisfied by the flight software block, which is owned by the software block, which is owned for the CUAV block. And we can look at it from the opposite point of view. We can take apart and ask what elements, what requirements affect this, the aircraft platform block, for example. We can see that it or its part properties, like powertrain or rotor, are connected to SysML requirements. And we can see exactly what connections occur. Or we can again go beyond that and look not just for its parts, but its parts, and go farther down the chain. And we see that now we have even more nodes, more blocks in purple, more SysML requirements in green, more JAMA requirements in gray that have been identified. As the number of different elements expands, we can also go to a tabular view of this to be able to look at the contents of this. In this particular case, we have a lot of different rows in the table, and each of those rows gives us the start, the definition. Finally, here we see these are the various JAMA requirements that are connected and affect the aircraft platform through at least two levels of part property association. We can also start to talk about requests that no longer are concerned with SysML elements, but this is a query that says, tell me all of the GitHub file commits that are affected by that JAMA search requirement. So in this particular case, there is one. We run the query, and we will see that there is a specific GitHub commit requirement, the one identified there, which is linked back to the JAMA requirement through multiple connections running across both intermodal and intramodal traces. We can even begin to ask such simple questions as, is one element connected to another element? And if so, how? And so this last example will do that. It says we have a block called aircraft platform, and we have a windshield part called battery. Are they connected? And the tabular result says, yes, they are. And it turns out that it's an indirect connection through multiple connection points, which are now explicitly displayed for the system engineer. This utility is offered in Syndeia 3.1 as a first step in demonstrating the power of graph database technology to support model-based systems engineering. Alternative databases and interfaces appropriate to multiple projects and users are being evaluated for future versions. To learn more about the latest features of Syndeia, visit our website at intercax.com or request an evaluation license. All of Syndeia's features and use cases are customer-driven. Contact us and let us know your requirements.